Okay, so welcome back. So we have the great pleasure today to welcome Jakob Salzer from the University of Brussels. He will talk about perspectives on quantum Carrollian field theories. So Jakob has been, before coming to Brussels, a postdoc at Harvard, and before he got his PhD degree in Vienna. He has been working on flat space holography and related topics for many years. He's one of the experts of the area, and he will talk about one difficult but very important corner of that flat space holography program, which is quantum Carrollian field theory. So, Jakob, please.
Yeah, thank you very much for the introduction. It's always a pleasure to have an occasion to come to Paris. And it's particularly nice to be able to speak at this historic institution. So thank you very much for the invitation, Marc. I'm going to talk about some of the results that appeared in these two papers that I had with these amazing collaborators of mine. Just a word on the title. It's deliberately chosen to be somewhat broad, a bit vague, in the sense that you will see that this is a difficult problem. And I think it's far from settled how to construct these quantum Carrollian field theories. So some of these perspectives that we have on this landscape will sometimes be a bit foggy, sometimes will be a bit clearer, and I think you will see when it's a bit foggy, but I will also make you aware of the open problems in this endeavor. So, yes, okay. Now, you've been following Marc's course on Carrollian gravity, but just for the benefit of everybody, let's make a small reminder here. So, what is the Carroll algebra? The Carroll algebra arises as a certain contraction of the Poincare algebra. In particular, what you do is you reinstate C and then take the limit C to 0 in the Poincare algebra. If you do this, then you find, first of all, that Hamiltonian and boosts commute, and second, that the boosts also commute with each other. Sorry, this is a typo here, of course. But boosts also commute with each other. The rest of the algebra stays the same. Now, what does this mean? This means that in the tangent space of every point, you don't have the Lorentz algebra acting, you don't have an SOD, 1, but instead you have these, since boosts commute with each other, you have an ISOD. Now, so this is just on the algebraic level, but you know that we can realize the Poincare algebra geometrically by giving you the Minkowski metric and then looking at the killing vectors of the Minkowski metric. So how can you realize the Carroll algebra? Well, I provide, as we just saw today, I give you a pair of a degenerate metric, which is flat in the spatial part, and a null vector pointing into the degenerate direction. Now we can look at the symmetries. So again, which vectors preserve this structure under the Lie derivative. And you find, as we just saw today, here, the spatial part, you get translations and rotations. And in this part, in the time part, you get, in principle, a function of the coordinates. So you get an infinite dimensional algebra. These are sometimes called supertranslations. Now, this is an infinite dimensional algebra. How can we get back to the global Carroll algebra? Well, what you do is you say that you want this function to be a linear function in Euclidean, in Cartesian coordinates. Then you find that the constant piece gives you time translation, and the linear piece will give you the boosts. And as we checked today, these Killing vectors close to the Carroll algebra. So you can also, this condition, maybe this will be mentioned next time, but you can also, if you require that, not keeping only these two tensors fixed, but in addition keeping the connection fixed, this actually produces this cutting down of the infinite dimensional group to the finite dimensional group. And then, as we just saw in the last 10 minutes, you can, this is the flat version of the Carroll algebra, but in the same way as you can make space-time curved if you have a Lorentzian geometry by just allowing for a Lorentzian metric, you can consider curve generalization of Carroll space-time by just providing this pair of structure. So again, a vector field and the metric where the vector field lies in the kernel of the metric. Okay, so why should I be interested in this? Maybe you've heard some motivation. So here are some motivations why we should care about Carroll structures. The first one is that if you think about any light-like surface in just a Lorentzian spacetime, the induced structure on this light-like surface will be a Carrollian structure. And indeed, we have many interesting light-like surfaces, for instance, horizons of black holes. So the induced structure on them is a Carroll structure. Then, which I think was the original motivation, one of the original motivations to study this, that the dynamics close to time-like singularities look like they're effectively happening in a Carrollian geometry. And again, time-like singularities is a very important topic in GR. Finally, you can consider hydrodynamics and take ultra-relativistic limits of them. Again, you will see these Carroll structures emerging. And finally, this is a topic that has come up in the past couple of years, which is that there are theoretical states of matter, so-called fractons, that also have some relation to these Carrollian structures. This is a bit more complicated, but this is just an additional motivation to study these Carrollian theories. Now, given this motivation, I think it's a very natural question to ask first, can we come up with field theories that couple to a Carrollian structure? The answer to this is yes, as we will see in a moment. But then secondly, can we also quantize them? And if we do this, what properties do these theories have? Okay, so this was, I think, already enough motivation to study Carrollian theories, but let me give you one more, which is the one why I'm mostly interested in this, and why this topic has picked up also in the last couple of years. Namely, if you think about an asymptotically flat spacetime, so something like Minkowski space here, an asymptotically flat spacetime has a very important null surface, namely future infinity or past null infinity. Now, this null infinity has a Carrollian structure. In fact, this has a bit less of a Carrollian structure. It has only a conformal class of Carrollian structures. So you find a pair, n and h, that should be identified if they differ only by some rescaling. And we know, so the Poincare group acts, so of course, the Poincare group is a symmetry group of Minkowski space. Close to the boundary, you have an action of the Poincare group on on null infinity. So you can regard the Poincare group as the conformal group of null infinity. Very similar to what I said before, you can view, if you look at the Killing vectors, or the conformal Killing vectors leaving this structure invariant, you find the Poincare group, but in fact you find a much, much bigger group, which is the Poincare group extended by so-called supertranslations. And cutting down this function, again, to its linear, to the 4 lowest modes, you recover the Poincare group. Now, in case you're familiar with asymptotically ADS spacetimes, the situation there is very similar. We have the conformal boundary of an asymptotically flat spacetime is equipped with a conformal class of Lorentzian metrics. And the ADS group, SO 3,2 in 4 dimensions, acts as the conformal group on this boundary. So the situation is completely analogous here. So there's this suggestion, this idea, is there a holographic description of 4D asymptotically flat spacetimes in terms of a conformal 3D Carrollian theory that couples to this boundary, to this structure, which means that it should be a Carrollian conformal field theory. Again, this is what you have in ADS. I mean, here in ADS we have there are examples coming from string theory that really show that we have this duality between gravity in an asymptotically ADS spacetime and a conformal field theory on the boundary, and we're asking ourselves, is there something analogous in the flat space case? So this is a huge program, but let me say that I think even if we're not able, even if this does not work out, which is a possibility, studying Carrollian CFTs should be useful, should have other uses. Namely, first of all, as we will also see in a moment, they provide a reinterpretation of scattering amplitudes in terms of correlation functions of this putative Carrollian CFT on the boundary. And maybe studying, so in this different formulation of scattering amplitudes, we will find some properties of scattering amplitudes which are obscured in the usual momentum basis. Then there is something that I'm very interested in at the moment. If you look at actual observables of asymptotically flat spacetimes, these are usual inclusive observables where you sum over outgoing states. Some of these inclusive observables have very nice interpretations in terms of extended operators living on scry, so-called detector operators. Now, since these operators are defined on scry, they should have a natural place in this Carrollian CFT, if we're able to make sense of it. And from this, we should learn something about the operators, about these detector operators. And then, even if nothing of this turns out to be true, if we are able to make sense of Carrollian CFTs, we have managed to produce a new class of exotic quantum field theories, which I think is of itself very important. And this will have an application for sure at some point. So some immediate questions. What are the properties of theories defined on this conformal Carrollian background? So what are the properties of Carrollian CFTs? I will answer this in a moment, or I will try to answer this. And then the second question is, can we explicitly construct such theories? And this is a bit more tricky. In fact, we don't have a good example at the moment. So here's the outline of my talk. First, I will discuss these conformal Carrollian theories just by using symmetry principles. And I will go through the things that you would usually do if you start to learn about conformal field theories, just usual Lorentzian or Euclidean conformal field theories. Namely, you study the basic fields, correlation functions, and try to understand what the OP is. But then, as I said, we're not able to find simple models to test these predictions that we make here. So what I will do is I will step away from the conformal case and just look at usual Carrollian field theories that are not necessarily conformal. Here we can certainly find some examples, and we will study these examples in detail and try to contest them and see that they also have some unusual properties. Okay, so let's start with this first part. Any questions? Please interrupt me at any point. So, the first thing is, what is the field content of these Carrollian conformal field theories? Null infinity has the structure of a homogeneous space of the Poincare group. I said there's an action of the Poincare group. In fact, it's a homogeneous space. And it turns out it's the unique homogeneous space of the Poincare group in dimensions 3 or lower. So this space is the unique three-dimensional homogeneous space of the Poincare group. You can just check this by looking at all the subalgebras of ISO 3,1. And there's just one 7-dimensional. So indeed, this is a 7-dimensional subalgebra. Let's check it. Here we have ISO2. This is the homogeneous Carroll group, as we just saw before, built out of 2 boosts in this case and 1 rotation. Then we have an additional generator, which are the dilatations, which I call dilatations. And 3 more generators that you can call special, in analogy to the Lorentzian case, you might call special Carrollian conformal generators. And then on top of this, so these are 7, and then on top of this we have usual the translations, temporal and spatial translations that move me around on this manifold. So let me emphasize that I've given these guys here some weird names, but these are really just generators of the Poincare algebra. So for instance, these, what I call boosts here, they belong to the translational part of the Poincare algebra. So having done this, we can follow the yellow book on CFTs and construct representations, primary, what we might want to call primary fields of this conformal Carrollian theory, namely by saying that if I give you the operator defined at one point in the space-time, I can define the operator everywhere else by moving it around with a unitary transformation. So it remains to define a representation here at this origin. In particular, I have to give you a representation of this of the stabilizer group here. And a natural choice is to say that these operators should transform in a spin S representation of SO2. So in particular, this will be just a helicity label plus minus an integer. I will only talk about bosonic field in this talk. And the dilatations here, this part just acts diagonally. And then all the remaining generators just annihilate the field. This would be what you call the primary conditions in a CFT. Yes, please.
This property that you mentioned, we know from standard CFTs, what are the basic assumptions behind it so that it can be generalized to more to situations, for example, where the algebra is slightly different? This is something that we have always been doing, of course.
Mm-hmm.
Right? So, but we have done it so much that we have forgotten the framework where it is really applicable. And I was wondering whether there are subtleties when trying to push it in the case of Carrollian structure. I have nothing bad in mind.
Yes, yes.
But I think because we are usually facing all sorts of trouble when trying to extend things in the Carrollian framework, maybe there are subtleties that we are just overlooking.
Mm-hmm. So I think with this construction in particular, I think this will become clear on the next slide, you recover basically Wigner massless particle representations, the Fourier transform of Wigner massless particle representations. So I think with this construction in particular, I don't think there's anything wrong. I'm not quite sure what could go wrong. There are certainly more general representations you can build here. And where, for instance, some of these fields, these generators here act non-trivially. And actually, yeah.
You may miss, this way one may miss some representation.
Yeah, you might miss some representation. And indeed, I'll come back later in the talk. I think this representation will not, I'm quite certain these representations are not enough if you want to make sense of Carrollian CFTs. Yeah.
Are you stating that not all representation are highest weight, is it correct? Something like that? Because this is the highest weight condition for the whole.
So I'm saying I could have a more general representation of the stabilizer group here. Not
the highest weight representation.
No, yeah, probably, yeah, yes. Okay, yeah. So if you do this program, this is the representation you get. So this is an intrinsic construction, just on Scry. But what you can do is you can I can also provide you an interpretation of this construction. Namely, consider some massless spin S field in the bulk, particularly here scalar field, and you push it to the boundary. By this I mean you multiply it by some powers of the radial coordinate and take the limit r to infinity, you can show that this object here transforms precisely in this case. Furthermore, if you're in Minkowski space and you have expanded this field into, you can expand this field into plane wave modes. So these would be really just creation and annihilation operators that create plane waves of a certain momentum, namely of a momentum pointing into the direction x on the celestial sphere. Then this operator here is nothing but a Fourier transform of this field here. So in this sense, and these create the usual Wigner massless particle states. So this is really nothing but a Fourier transform. As I said, so in the ADS, using some ADS language, we might call this an extrapolated dictionary. I can, from some bulk fields, I can extract a representation, a field on the boundary. You can also, as I mentioned briefly, and I might come back to this later, one can also consider other indecomposable representations of of the algebra we had before, and I believe that they are important if we want to make sense of these theories. Okay, so we defined our basic building blocks of the theory. Now we do the next thing that you might want to do if you learn CFTs, namely you want to compute correlation functions. We assume that we have a Poincare invariant vacuum in this theory. And then we demand that primary correlation function of these primary operators should be invariant under the Poincare group. So basically this is just an exercise in solving differential equations. Now if you do this exercise, you see that the crucial generator that crucially determines the structure of the correlation functions is the boost generator. This is no surprise because it's precisely the boosts that differ from the usual Lorentzian case. If you do this, so if you solve for the 2-point function, you find that you have two options. The first option is that the 2-point function is U independent. So you're basically just killing, so it's U independent. Then the only constraints that you have come from the SO3,1 part of your Poincare group. Remember that SO3,1 acts as the conformal group on a 2-sphere, so the correlator you get will just be the usual correlator we know from 2D CFTs. This is a bit boring, but so you're looking for more solutions, and what else can you get? So the other solution you get is something that vanishes when you multiply it by x. So it turns out that we have to consider distributions in this case. So there's another distributional branch which is proportional to a delta function. So these operators basically have to sit on top of each other on the spatial slices. But then you can have some non-trivial U dependence. So these are the 2-point functions of this theory, and we see already that the structure is much richer, or not much richer, but it's richer than in the usual CFT, where, I mean, actually we also have contact terms there, but we discard them. Here, we don't want to discard them, as we will see in a minute. Okay, so you can go on and do this exercise further, solving these differential equations. Here is the 3-point function. Again, you find that if you want to have something that is time dependent, all of these three operators have to sit on top of each other. You can also have always the time independent solution, which will be just the usual CFT 3-point function, which is a polynomial in the spatial coordinates. Now, generically, these are the only options you have. But in the case where the base, so we're talking about 3-dimensional scry, the base space is 2-dimensional, we can do something more. Namely, we can introduce complex coordinates on the base space, z and z bar, but allow them not to be conjugate to each other. So we basically complexify our space-time. In this case, there's one more solution, namely that you have a delta function in one of these directions and a time-dependent and spatial dependence in the other direction. Why would I want to do this? If you think about scattering amplitudes, 3-point scattering amplitudes in Minkowski spacetime right now, then this is precisely the right thought. I will come back to this in a minute. And then finally, so these are these are uniquely determined up to some numbers, like we have in the CFT. Then you can look at the 4-point function. I think that this has not been completely solved yet, the problem, but the most complete solution I know is here, which is, again, something distributional and some kinematic factor times a function of two invariants, conformal cross ratio and some Carrollian invariant combination of coordinates. So again, very similar to the CFT case, where the 4-point function is defined up to a conformal cross ratio, a function of the conformal cross ratios. Okay. Now, we determined these correlators. Can we make a check on them? And the answer is yes. So if you remember this extrapolate dictionary that I had, that I told you about, we can relate Carrollian correlators to momentum space creation and annihilation operators just by a Fourier transform. So if you think it's about this, you come to the conclusion that if you start with a scattering amplitude, where you parameterize your momenta again in this way, so by some energy times a reference null vector that points to a point x on the celestial sphere. If you take the scattering amplitude and hit it with this, people call it sometimes generalized Fourier transform or a generalized Mellin transform, but you can set delta equals to 1 if you want. Then you end up with a correlation function that transforms precisely as a correlation function of primary operators in a putative Carrollian CFT. So you take your favorite scattering, 2, 3, or 4-point scattering amplitude, you hit it with this transform, and you can reproduce precisely correlators of this type here. And so going back to my comment about 3-point functions, you might remember that 3-point scattering amplitudes in Minkowski space of massless particles are strictly 0. But if you're allowing yourself to complexify your momenta, you find these 3-point MHV amplitudes, which are the building blocks of all higher point tree level amplitudes, and they are precisely of that form here. So indeed, it turns out as I said before, we don't want to, and the other solution for 3-point amplitudes is, of course, that they're completely collinear, which would correspond to this branch here. So 3-point scattering amplitudes in Minkowski space, massless 3-point scattering amplitudes in Minkowski space are either 0 or completely collinear, unless you allow yourself to complexify your momenta. We shouldn't discard this. So this distributional branch is actually the branch that's related to hard scattering in the bulk. Okay, this was correlation functions. So we hard, yeah, to hard.
From the bulk perspective, I suppose, this is what you mean.
I mean, yes.
Most correlators on the boundary would correspond to phenomena that are hard phenomena in the bulk.
Yes, right. So these are fine. I'm scattering finite energy particles in the bulk. Okay, so we ticked off these two first points of Carrollian theory. We already see that they're a bit less rigid and more intricate due to these distributions appearing than usual CFTs. So let's try to see whether we can make sense of an OPE. So the question is there a convergent Carrollian OPE? Which, of course, if you think about usual Lorentzian CFTs, a convergent OPE is kind of is the word. I mean, it's one of the most important properties that you have in the CFT. So do we have something similar here? And I would say that the answer to this is not clear at the moment, but I can provide you with at least some hints that we have that this OPE will have some difficult, strange properties. So we assume that we have two operators, O1, O2, and we bring them close together. Then we can expand them into a sum of other conformal Carrollian primary operators times some OPE structure. And then we have subleading terms and other terms that I will come back to in a moment. So first of all, these OPE structures here in the usual CFT, we know what this is. This would be just some polynomials that depend, whose power depends on the conformal weights of these operators here. Here we see that we might have expected, since we have the 3-point functions that we have are distributional and more rich, we also have more options for this OPE structure here. We can have this ultralocal branch or these chiral branches. Okay, so there's no unique 3-point function, which means that there are also several OPE branches. Second is that in a usual CFT, if you take just one primary operator, all the subleading terms are completely determined by the action of the conformal group on this primary operator. So the subleading terms are given by descendants of the primary operator. This it turns out to be a bit tricky here in this case, because there is kind of we find there's no absolute primary for a Carrollian OPE block. If I say that this operator O1 and O2 fuse into an operator K with a certain weight, sometimes I have to assume that there are certain parent operator or ascendant operators whose derivatives equal K, so they would have weight delta K minus N. And the descendants of this parent operator actually mix with the descendants of the original operator, all contributing into the subleading terms here. So, and this happens apart from very fine-tuned situations. In the next slide, you will see an example of this. So already we see that here in this U direction, it's this OPE, in the U direction, the OPE is not really local, apparently. And then, what are these additional guys here? If you act with the Casimir on the left, you will find that the quadratic Casimir, which gives you the mass, if you act on this on the left, then this is non-zero. And it's non-zero precisely when these two operators have a finite spatial separation. But if you act on it on the right, all of these representations are strictly massless. So you will produce a 0 here on the right-hand side. Which means that if you go just infinitesimally away from the strict x squared equals 0 limit, then you need operators that have a non-zero Casimir, which means that you need massive operators. And these are these new operators that I said at the very beginning that we are apparently missing. But you can construct them as an indecomposable representation of the Poincare algebra. So let me, just to give you some formulas, let's focus on this chiral branch here. So this is, suppose we have two operators with weights H1 and H2 fusing into an operator H3. And we assume that they have this chiral, they have an OPE structure, a leading OPE structure of this chiral branch here, of this chiral type. Then assume first that this coefficient here is 0. So the power here is 0. So we're in a fine-tuned situations where these three operators, the weights of these three operators obey this equation. Then you can compute explicitly, you can compute all the subleading terms here. I can compute all the subleading terms, and they're indeed just given by descendants of the original operator 3. And these coefficients are just determined in terms of a beta function, as is the case in the usual CFT, 2D CFT. However, if you go away from this kind of fine-tuned point, it turns out that you will have to include, so I call this parents will get involved. So say this operator O1 and O2 fuse into an operator 3, and then just from consistency of the Carroll algebra, it turns out that you will have to include a descendant, so you will have to include the descendant of one of these guys, where this is basically the integral of O3. And then having this one, you will have to include that one, and this goes on all the way up the ladder. Of course, all the way up the ladder of use, basically. Of course, it also goes all the way down to use. So we see already that this is what I meant before. Except for this fine-tuned situation, there is, in the U direction, this theory seems to be a bit, the OPE is non-local. Indeed, you can write an integral version of this OPE block. So these OPEs are a bit strange. I think, as you see here, they are not completely understood, clearly not completely understood. But what you can do is you can check from explicit examples from scattering amplitudes that these OPEs are, you can reproduce OPEs of that type. What I mean by this is you take your favorite 4-point scattering amplitude, you hit it with this Fourier transform that I told you about. By this you recover a 4-point function of this Carrollian theory, and you take two of these operators together, and you indeed recover these OPEs here. So they pass this first check, but on general principles, they're not really, I would say, completely understood yet. Okay, so this is kind of the summary of this first part. Conformal Carrollian primary fields can be constructed in analogy to the Lorentzian case. These low-point correlation functions have time-dependent distributional solutions and time-independent CFT solutions. The 2, 3, and 4-point functions, there are 2 and 3-point functions are fixed completely up to a coefficient. I mean, you have several solutions, but all of them are fixed up to a coefficient. The 4-point function is maybe not the most general solution, is not yet known. We can relate them to scattering amplitudes, which reproduce these time-dependent distributional correlators. And then, as I just told you, this Carrollian OPE seems to have several branches and is certainly less constraining than the Lorentzian version, precisely maybe because we have this non-locality in the U direction.
Is the OPE associative?
Very good question. It actually occurred to me a couple of days ago. I have to admit we haven't checked it yet. But I had the same idea just a few days ago that we should check it. I think this one probably is. This one probably is. But yeah. Okay. So now I gave you these constructions just based on symmetries. There was no dynamics, just kinematics and symmetries. Now, now the question is, can I give you a simple example of a Carrollian CFT where I can go and check all of these properties that we just found by just symmetry arguments? And the thing is that so our knowledge in general about these Carrollian CFTs is somehow indirect in the sense that it just relies on symmetries, as I just discussed. You can basically construct Carrollian correlators from scattering amplitudes, but then you have to assume that this dictionary is the correct one. You can certainly construct Carrollian correlators by taking limits of correlation functions of usual Lorentzian CFTs, basically taking again some C to 0 limits. You can also think about the stress tensor in Carrollian CFTs, which was done in this nice paper. But we don't have any concrete example of a Lagrangian where you can go and just compute correlation functions. In the same way as you can, for instance, in a Lorentzian CFT, you have all these nice axioms about CFTs, but then you can go and take the Wilson-Fisher CFT and just start computing order-by-order in perturbation theory, and you will find that all of this is indeed true. Here we don't have this freedom yet. So what I want to do in the next part is it's always difficult to find conformal Lagrangians, right? I mean, even having Lagrangians for usual Lorentzian CFTs is not easy. So maybe we should first try to understand non-conformal Carrollian theories, where we can come up with examples, and then study them and see what kind of structures we get. So in some sense, maybe we should, before we start learning CFTs, we should learn the Carrollian version of Weinberg. So this will be the next part of this talk, and let me say that these papers also did some very nice work in this direction. Okay. Then, yeah, please, if you have any questions, interrupt me at any point. Now I will go on to this second part. Okay, so Carrollian field theories. How do we come up with Carrollian field theories? There is the defining feature of Carrollian field theories, maybe this will come up in this course later at some point, is that the Hamiltonian density, if you take the Hamiltonian of the theory and then look at the Hamiltonian density, the Hamiltonian density commutes with itself at each point in space. And this indeed, you can show that this implies chiral invariance. This is very different from the Lorentzian case, by the way. So what does this mean? This means if you have an action in the Hamiltonian form, so pi phi dot minus the Hamiltonian density, you can, just based on this criterion, you can construct a chiral invariant theory. The first solution is that you say, let's make this Hamiltonian independent of the momenta, so it depends only on phi, and then you will know, it certainly will commute with itself at each point in space-time. These theories of that type are called magnetic Carrollian theory. There's also the other option that you say it depends on pi, but then it turns out it cannot depend on, at least for these simple theories that we're looking at, on the gradient squared. So the gradient squared term drops out. These theories are called electric Carrollian theories. The most general theory is, of course, a combination of these two, but we will go on and study them separately first. And let me stress that both of them you can see as from limits of relativistic theories, which was studied in that paper here. Okay, so let's start with these electric Carrollian theories. Here, to prove the point, we focus on a very simple class of theories, namely two-derivative scalar theories. So what are they? So they have just, you have the momentum squared, du phi squared, and then some potential. And then let's look at this the simplest example, which is just that we take this potential here to be quadratic. Then you assume now the existence of a vacuum, of a chiral invariant vacuum, and you can expand this field phi again into modes. So you just do canonical quantization. However, the important difference here is that the energy of all of these modes is independent of this spatial vector k. Precisely because there is no derivative term here. So all of these states have the same energy. This theory, so it's highly degenerate. These are sometimes called theories of flat bands. I mean, if you remember the usual, because the dispersion relation is just flat. So all of these states have the same energy, and you can also look at something like the free energy. You will find this would be the relativistic case. You have the Matsubara frequencies, and then k squared, which is absent in this case. Now, but then you still have to do this k integrals here, but they have nothing to integrate over. So what they will give you is just a divergence a to the minus d, with a some uv cutoff. So you see that we have some uv divergences that we have to take care of. Similarly, if you start to do perturbation theory for these theories, we have all the loop integrals will diverge as a to the minus dl. So these theories clearly need some regularization. Okay. As always, there are probably many choices to regularize theories. Here, in our case, we chose the simplest one, which is just put them on a lattice and see what you get. So indeed, we just get sums over quantum mechanics. At each point on this lattice, on this spatial lattice, there's a quantum mechanical model, a quantum mechanical action for some quantum mechanics sitting. So we have a sum over these lattice points here, where these fields are called, in order for this action on each lattice side to have canonical dimensions, we rescale these fields. So we call it phi tilde a to the minus d over 2 times phi. Now we assume that on each lattice side there's some polynomial potential, some quadratic potential, cubic, whatever. And now you can go, and this is just an exercise in quantum mechanics, you can start doing perturbation theory. So you have your propagator, which is just a free, so we assume there's a mass there, which is just a free propagator, 1 over omega squared minus m squared. Notice that I did the Fourier transform here, so I'm in a mixed case where I'm in position space on the spatial part, but in Fourier space on the time part. So these fields, it's a Fourier transform, e to the I omega u. And of course I have a delta ij here because these quantum mechanics don't talk to each other, right? I mean, everything is just happening at one point. So you can do perturbation theory, you have the propagator, it's corrected by some self-energy if you have a cubic coupling and so on. Similarly, you have a non-vanishing 3-point function, lambda 3, if you have a cubic coupling lambda 3, non-vanishing 4-point function, whatever, so whatever you put here. Okay, that was very simple, but this is still on the lattice, and we want to get back to the continuum description. So what we want to do is we want to undo this rescaling. We go back to the phi variables, which are rescaled versions of this phi tilde, which are the quantum mechanics on each point, and set the lattice to 0. So we have this propagator from before gets now just multiplied by 1 over a to the d, which in the continuum limit gives you a delta function. This is nice. This is just what we expect. This gives you some distribution. Some spatial part has this distributional dependence, precisely what we saw in the Carrollian CFD case. And it will have some U dependence. Similarly, if you have a cubic coupling, this will get corrected in perturbation theory. So indeed, we get a finite ultra-local 2-point function corrected at each order in perturbation theory. Notice some peculiarity here is namely that I have to, in order to compute this 2-point function, I actually have to provide you all the couplings here of the quantum mechanical model at each side. So infinitely many couplings contribute to this 2-point function. Okay, this is nice. This is precisely what we wanted, what we expected. But let's go now and check the 3-point function, where we again want to have some ultra-local 3-point function. And indeed, you find that the 3-point function of this field is proportional to lambda to the 3 times some spatial distributions. But if you really do the continuum limit, send a to 0, all of these higher point functions vanish. So the upshot is this. Simple electric Carrollian theories produce distributional correlation functions that we also saw in the conformal case, corresponding to the scattering of hard particles, but they can only describe generalized free fields in the sense, what I mean by this is that the 2-point functions get corrected at each order in perturbation theories, but higher point functions are 0. So this regularization that we got is nice in the sense it got rid of all the problems of the UV divergences, but it might be too strong. I mean, it's too strong. We get rid of all dynamics, apparently. So I would say it's still an open problem how to define an interacting electric Carrollian QFT and even better conformal Carrollian QFT. Just a disclaimer, as I mentioned already before, so these 3-point function, 4-point functions, they can be reproduced from a limiting procedure. If you start with a relativistic QFT and you take some limits, you can obtain some correlators that obey the word identities, but again, we don't have an intrinsic construction of them. Okay. So in the very end, I will provide you with some ideas how to proceed here. But let me now turn to the magnetic Carrollian theories. So what is the magnetic action? The magnetic action is just this, so this is pi chi dot, what I call pi, I call q now here. So this would be the momentum. Then times a Hamiltonian, which is completely independent of the momenta, so it's independent of q. Since it's independent of q, you see that on shell, if I vary with respect to q, the chi's are constant, right? So the chi's are constants of motion. This tells you that you can, these chi's here, they form a nice basis of states with an inner product that you can argue is a delta function. So these are like infinite dimensional versions of usual momentum states that are normalized to delta functions. Here they are normalized to delta functionals. We have energy eigenstate, so all of these are energy eigenstates. So acting with the Hamiltonian on them, you obtain just the energy of this chi configuration that you're looking at. But also notice that here nothing is really quantum, right? I mean, I haven't quantized anything. We have this continuous spectrum of energies. Okay, so what I can do now, what are nice observables in this case? I can look at the partition function, for instance. So z of beta, which is I define as a trace over all the states, e to the minus beta h, h being the Hamiltonian. So of course, I have to provide you. So I can do the trace since I gave you this basis of states, these chi's. I can do this. These are all eigenstates of the Hamiltonian, so acting on them with the Hamiltonian just gives me the energy. I still have to do this path integrals over the chi configurations, but you see that I have a chi hitting this other chi, which will just give me some delta functional, which is an R divergence due to this continuous spectrum of states. However, this other piece here has a very nice interpretation just as a partition function of a statistical system in one dimension lower. You can generalize this and consider other observables, which would be something that you might call in the usual case correlation functions at finite temperature. So trace rho beta times the strings of chi's, and again you can write it in terms of they look like a statistical system, and they look like statistical correlators. So the upshot of this is magnetic Carrollian theories behave in many respects like Euclidean systems of one dimension lower. Let me tell you that, these expressions here, these chi's being a delta function of chi's, and this measure here, it's somewhat formal, right? I haven't given you a definition of this. So defining a theory means also defining this measure and making sense of this delta functional here. Actually, there's a very nice example. I think I don't have the time to go into. I don't have the time to go into this, but I'm happy to tell you more about this. A very nice example of this is if you look at 3D gravity in flat space. Gravity in 3 dimensions does not have any propagating degrees of freedom. It only has boundary dynamics. And what you can do is you can reduce the dynamics of 3D gravity to the dynamics on orbits of BMS3, which is the asymptotic symmetry group of this 3-dimensional flat spacetimes. So you can reduce the dynamics of Einstein gravity to dynamics to a 2-dimensional action on these orbits, and it turns out that you can write this precisely as a magnetic Carrollian action. What is nice about this, that in this example, the fact that the dynamics happens on this BMS orbit gives meaning to this functional measure, and also to this measure here and to this delta function of the states. So in particular, you find that the partition function of 3D gravity, 3D flat space gravity, yields this delta function here, delta functional of 0, so a huge IR divergence, but then also a finite part made up of a saddle point contribution and a one-loop contribution. More generally, you might expect that this magnetic sector is, again, if we think about some holographic duality, that this magnetic sector is a natural candidate for the soft modes or edge modes. Indeed, in 3D gravity, the only thing you have are edge modes. Okay, now we're still on a quest to find an interacting Carrollian theory. So one might say that maybe we should couple together an electric and the magnetic sector, and this will give us some nice and interesting dynamics. This is what we did in the paper, so we considered several examples, one of them being Carrollian electrodynamics coupled to matter, the other one being this theory that I show you here. So this is a free electric Carrollian theory and a magnetic theory here, together with a Yukawa coupling. So again, you have to regulate the divergences. We do this by introducing this spatial lattice of side A. You can compute many correlators. I don't give you the formulas. They're not very illuminating. You can find them in the paper. But you can do some expansion to Feynman diagrams. But again, it turns out that in the continuum limit, all of these correlation functions go away, which is a bit unfortunate. Okay, with this, let me conclude. So, for the first part, these conformal Carrollian theories, they are theories tailored to the natural structure of null infinity. These are theories that couple to the conformal Carrollian structure of null infinity. So if there is some duality, they seem to be natural candidates, but as I have argued, I think they're also interesting to study by themselves. The symmetries determine 2, 3, and 4-point functions with 2 branches. The time-dependent branch, distributional branch, can be related to S-matrix amplitudes. And some pieces of a potential OPE expansion are understood, but clearly much more needs to be done in order to see whether there's really such a thing as an OPE expansion. Now, some question, as I said, is an important one. Can we define a convergent OPE expansion? Is the OPE associative in all cases? It's a good question. What is a good basis of operators for a Carrollian OPE? We have these primary operators. I mentioned that we probably also have to include operators that have non-zero Casimir, which are called massive operators. There is also the stress energy tensor, and so the stress energy tensor multiplet that you have to include. Is there more? What's the role of supertranslations? So null infinity has much more symmetries than what I used here. In my talk, I only used kind of the global part, the finite dimensional part of the conformal Carroll group, which is Poincaré. But I didn't talk about supertranslations. So what role do they play? Would be very interesting to make some relation to this recent discussion about BMS representations and how they can help to come up with IR finite scattering amplitudes. And then I said that it's difficult to find explicit examples of Carrollian CFTs, so what we did is we turned to non-conformal theories, where we studied simple systems of electric Carrollian theories. They give us these contact term solution correlation functions that we expected, at least the 2-point functions, but only the Gaussian correlators remain. Higher point functions are 0, but the 2-point functions get renormalized at each order, get corrected at each order in perturbation theory. Then we had these magnetic theories, which seem to behave like Euclidean systems in one dimension lower. We studied coupled electric and magnetic theories, but again, there are also only the Gaussian correlators remain. So I would say it's still an open problem. Can we define is it even possible to define an interacting Carrollian theory, or even better, an interacting conformal Carrollian theory? Or do the quantum theories, the classical theories, they exist for sure. We wrote down, Marc wrote down some Lagrangians. But the quantum theories, if you need to regularize all divergences, can you do this in such a way that you don't only get Gaussian correlators? So we only looked at very simple. So okay, there's no example as far as I know of in the literature. So let me give you some ideas where we might want to look. So first of all, we looked at only very simple theories, right? I mean, the theories we looked at are the simplest ones that you can imagine. I mean, we coupled these theories together, which is a bit less simple, but still it's, still rather simple. Maybe we have to consider more intricate models. For instance, this one looks very interesting. This model came up actually from 2 papers coming from 2 different directions. And you see here that you can have spatial derivatives here. This is, you might want to call an electric Carrollian theory. You can have spatial derivatives, but you have to have this interesting Carrollian invariant term here. So maybe we have to quantize a theory of that type, and then we will find something non-trivial. Yeah, I don't have much to say about this other than we had a quick look and we weren't, there was no immediate easy way to do it. Maybe we need more elaborate couplings between magnetic and electric theories. Again, we just looked at this simple Yukawa coupling. We looked at a minimal coupling between electrodynamics and matter. Perhaps this is the way to go, couple them together in a more interesting way. Perhaps there's also, maybe we have also too much symmetry. So these electric theories that are presented, they have a lot of symmetry. They have Carrollian invariance, they have actually super translation invariance, but they also have invariance on the volume preserving diffeomorphisms, since all the points decouple. So this is clearly a lot of symmetry. Also, so this model, I think this has super translation invariance as well. So maybe we need to break some of this symmetry, either explicitly or spontaneously in some way, because maybe the symmetry is preventing us from getting interesting dynamics. But yeah, maybe after following the course of Marc, you will come up with another idea and you will find a good solution to this open problem. So thank you very much.